There are more seats. There's more seats. You're not really supposed to sit in that table.
Yeah, these are for the latecomers. Fill the seats if we can.
There's more seats.
Don't be shy right there. Better to cross the speaker now than when you start.
Otherwise, the tomatoes get directed at them, right?
That's right. We just did that great ones.
Never mind, he's doing worse.
I have a meeting with Bill at 11:30.
In that case, that's a good spot for you.
So, Boo, you sit over here.
No, I'll sit here.
Okay, I think you're right.
All right, so thank you everyone for joining us for our guest lecture. The IEEE PES IAS chapter is excited to welcome Christina DiMarino to speak with us today. Christina received her bachelor's in electrical engineering from the James Madison University in Virginia in 2012 and joined the CPAS Center, the Center for Power Electronic Systems at Virginia Tech, where she received her master's in 2014 working on high temperature silicon carbide transistors, and has continued with this work focusing on high density packaging for 10 kilovolt silicon carbide MOSFETs, which she'll be sharing about today. She works towards her PhD at the CPAS Center at Virginia Tech. Outside of the lab, she's very involved with the national PELS group, the Power Electronics Society, in several functions, as well as she restarted the PELS chapter at Virginia Tech. So she'll be sharing both about her experiences and initiatives with PELS, as well as some about her research. So please join me in welcoming Christina DiMarino.
Thank you. Great. Thank you all for coming. So I'll start with a brief background about CPES and the work that we do there, and then go into the more detailed technical talk about my research, specifically focused on 10 kV silicon carbide MOSFET power module packaging. And this work is actually done in collaboration with the University of Nottingham. So they also have a very strong packaging group there, and power electronics and machines and control group as well. So a little bit about CPES. We have right now about 6 faculty, and we have a mix of graduate students. About the majority are doctoral students, and in total we have a little bit more than 50 students, and that's growing. So, and at any given time we have between 10 and 15 visiting scholars, both from industry and academia. So we were also for 10 years an NSF Engineering Research Center, and once that ended, kind of some of the funding went away, so the number of people declined a little bit, but now we're starting to ramp back up, and we're hiring new faculty every year, and with that also more students. So actually we have 2 CPES locations now. So we've got the main CPES location is in the Blacksburg campus of Virginia. So for those that don't know Virginia, Blacksburg is in the kind of southwestern part, very close to West Virginia. And there we've got several CPES labs, about 20,000 square feet in total, including office space. So we've got the standard power electronics labs with every student gets their own monitor too, so they can share their research as you're giving tours. We have several high power testing bays, so especially for this high voltage kind of work, you need to make sure that everything is closed off and safe. We then also have kind of some more unique labs. We've got a power electronics packaging lab. So in there we've got some specialty equipment like some wire bonders, lasers, stuff for silver sintering, soldering, thermal cycling chambers for assessing reliability of your systems as well. And then we've got a new lab that we're designing in the Northern Capital Region, they call it. It's in Arlington, Virginia, very close to DC, about 20 minutes outside of Washington, DC. So there we want to have an even more kind of modern, design-oriented power electronics lab. And a lot of our higher power research will be in that area in the future.
When you said every student gets a monitor, what does that mean?
So every student has their own bench in the CPES electronics lab, the main power electronics lab, and they each have their own TV monitor above their bench. So they've got their standard computer, and then that links to their TV. And so when it's nice for when you're giving tours. So that way, well, it acts as a separate monitor for the students. So they sometimes run simulations on one and are working on the other. And then also, it's nice so that when we're giving tours, and we give tours almost every day to a new company or someone from academia visiting. So this is just a place for students to display kind of their electronic posters of their research, and that way they can update it more frequently. Yeah. So SI PES has been doing this for quite some time, and they love it and want to keep doing that. So even in the new lab, we're also going to have monitors and stuff there as well. It's just a nice way to kind of get an overview, because there are 50 students in the lab, and so to be able to, it's hard to remember what every student is doing when you're giving a tour. So that's kind of a nice way to do that. Okay, so the research areas of SI PES, everything from a few watts to megawatts. So we work a lot in transportation electrification. We've got about 80 industry members, and a lot of those are from car manufacturers, aerospace, and also naval ships. We then also work a lot on kind of more emerging technologies like wireless power transfer for electric vehicles as well as consumer electronics. A lot of data center work recently has been ramping up, and also higher power electronics as well, things for renewable energy integration, STATCOMs, FACS, medium voltage converters, and other things for the power grid. And so with that, our technology areas, we've got the traditional kind of power electronic areas. So you've got your power conversion topologies and architectures, modeling and control. So those are pretty standard. Also EMI and power quality. And then when we got the NSF ERC, we kind of added these two parts with the power electronics components, and in particular the high density integration. And that's where the packaging lab really comes into play. And that's my area of focus. And so to really keep up with all the changes in these dynamic fields, in these growing fields, we've really been looking at more and more into wide bandgap semiconductors, and that's because of their beneficial material properties. So I apologize for those that already know it, but just a quick background about wide bandgap. So standard power semiconductors are made of silicon, and gallium nitride, or GaN, has some material properties that add some additional benefits, and silicon carbide has some further material property benefits as well. And so what does this actually translate to for designers? So if you have a high electron mobility, high saturation velocity, and high electric field, you can get faster switching speed, and you can get lower on-state losses. So when you're conducting current, you can have lower power loss. And so at Silicon Carbide, I designed a power module that's capable of operating at 99% efficiency. And this was for a solar application and sponsored by RPE. But we also have students that have demonstrated full converters with Silicon Carbide operating at, I think it was 99.5% and 99.6% efficiency. Those were for aerospace applications. Then another feature of silicon carbide is its wide bandgap, obviously, hence the name of these materials, and the high thermal conductivity, which means that it can operate at higher junction temperatures. So we had a project with Rolls-Royce to design a 50 kilowatt AC to DC bidirectional converter that could sit in the jet engine compartment. So it needed to be able to operate at ambient temperature of 200 degrees Celsius. So we actually had to custom design a power module. At that time, none were commercially available, with silicon carbide MOSFETs capable of operating at 200 to 250 degrees C. And then also the nice, yeah.
What about the other auxiliary parts, gate drivers?
Right. So at the time, we used a gate driver from CSOID. They had come out with a high temperature gate driver. Controllers, the controller we used, we ended up having actually external to the circuit. Because TI had just come out with a high temperature controller at the time of this project. So we just said, okay, in the actual application, you'd be able to use TI's high temperature controller. But everything else, the sensors, everything, they were all high temperature. Yeah, from Honeywell and CSOID companies like that, yeah.
Roughly what power density numbers, you know what they are?
For this converter? Yeah. I don't remember the exact size of the converter. It was it's approximately this big and 50 kilowatt. So yeah. Any other questions? Okay. And then, so because of the high electric field strength of silicon carbide, you can actually also obtain higher voltage silicon devices. So this is a single semiconductor device that can block 10,000 volts. And they've also demonstrated up to, I think it was 27 kV capable of blocking voltage. So that's something that silicon cannot go anywhere near. Anything above 6.5 kV for silicon IGBT, it becomes just too lossy. It's not worth doing. And so we actually got our hands on the first generation 10 kV 120 amp power modules. And with that, we built these kind of what we call power electronics building blocks, or PEBs. And this is kind of a concept that was developed by the Office of Naval Research some time ago, actually. And the idea is that these are just modular units that can act by themselves, or you can put them in series or parallel to scale the current or voltage of your power electronic system. And that way, it's just really easy for people to perform maintenance on these components and to scale them to whatever to fit their system needs. And so we did that with these 10 kV devices. But in order to achieve these numbers, you can't just have the semiconductor themselves. You need a way to package them and to incorporate them into your system. So for fast switching speed, you need to have low parasitic inductance. For high temperature operation, you need to obviously have temperatures that are capable of operating reliably under high temperature conditions. And for high voltage, when you want to get high density, you need to worry about electric fields. So if you have electric fields that are too high in certain areas, you could get very high energy discharges that'll degrade the dielectric materials in your system. So new packaging technologies are needed in order to realize the full potential of these wide bandgap devices. So what do I mean by a power module package? So typically it consists of some sort of heatsink or thermal management system. So this is a standard just finned heatsink. Then you've got your thermal interface material and your insulating substrate. So this is what isolates your circuit, so your semiconductor devices, from your cooling system, electrically isolates it. It's typically made of a metal laminate. Then you've got your die attach and your semiconductor die. And then the interconnection is usually done with wire bonds traditionally. And then you've got your terminals, and finally your encapsulation. The encapsulation just helps with your dielectric properties. And so these are kind of standard packaging technologies that were developed for silicon. They work well for silicon for the most part. They also kind of have some issues there, but they're especially not optimal for wide bandgap devices. So some of the challenges that are common in power module packaging are that parasitic conductance can cause significant voltage overshoot as well as ringing in your circuit. So this is seen just from the equation, voltage equals inductance times your rate of change of current. Then asymmetrical parasitic inductance is also an issue. So in order to increase the current of your power module, you need to put multiple semiconductor die in parallel. And so here's an example for silicon IGBT. So there are 6 die in parallel, 6 IGBTs in parallel, and this is the terminal to the rest of your system. So this is a look at the turn on transient. So this is your current here. So you can see that die number 6 is the farthest from the source terminal. So it has the highest parasitic inductance, and hence during the transient, it has the lowest current overshoot. Whereas die number 3 is the closest, and so it has more than 2 times higher current overshoot during the turn on transient. And this is significant because then that means the switching losses are not symmetrical for all the die. So the heating is also going to be different. A further issue is the parasitic capacitance. So across that insulating substrate, there's an inherent capacitance. And so under high dV/dt transients, now you can get common mode currents flowing through your system ground, which is also significant. And of course, these are all intensified for wide bandgap devices because of the high-speed switching, the higher dI/dt and dV/dt. In addition to that, you have further challenges when it comes to high voltage packaging. So now you have to also worry about electric fields. So I mentioned this briefly before, but in particular, if you have a very high electric field concentration, you can get what's called partial discharge, which is a very high energy event. And you can actually, if you see it, you can actually see it. It's a spark that occurs, and you can even hear cracking in the air when it's breaking down air. And so this is primarily a concern in your insulating substrate, which does the majority of the blocking the voltage in your power module. So this is a cross-section look. So you've got your metal substrate. And if you apply, for instance, 10 kV across this, then you can see that in the bulk of your ceramic, the electric field is pretty uniform, and it's exactly what you would expect. Your voltage over your distance. But where your metal, ceramic, and encapsulation meet, so the encapsulation is again for improved dielectric properties, that's where you get your significant electric field concentration. And that's actually called the triple point. And that's where your partial discharge will occur. So this is an example of a real substrate, a metal, ceramic, metal substrate, where repetitive partial discharge was occurring at these triple points, and it actually led to cracking of the ceramic. So then that completely destroys the isolation from your heatsink, and now your module and your whole system could be damaged. So it's really essential that in these high voltage modules, especially if you want to achieve high density, you need to make sure that the electric field at these triple points is well controlled. Another thing for higher power applications is high energy absorption. So when you have a fault, you need to make sure that you're able to handle that higher amounts of energy. And this is primarily a concern with the interconnection. So wire bonds in particular are not known for being able to withstand high amounts of energy. So at maybe 63 joules, the wire bonds here are still intact. You increase that to 500 joules, and you can't even see the wire bonds anymore. They're completely gone. And now that's an open circuit failure mode. So that's not always optimal for certain systems. So that's something that also needs to be considered when looking at higher power applications. And then finally, electromagnetic interference. You do get this in lower voltage as well, but it's also very critical at high voltage. So I mentioned these 10 kV power modules before and how we put them in a PEB, a power electronics building block. Well, when we went to operate the power electronics building block in a normal converter operation, actually the maximum voltage, they were supposed to operate at 6 kV. Maximum voltage was limited to less than 3 kV because of significant EMI issues. Actually, we were getting that all the protection signals were triggering when there was no fault on the system, and even some control components were blowing up. So when we were operating, we had about 100 amps average current on the load. And the current through the ground we were getting peaks, 200 amps peak to peak, flowing through the system ground. So it was quite significant. And part of that reason actually is that this power module package was designed for silicon IGBTs that switch more than an order of magnitude slower than these silicon carbide MOSFETs. So now you've got the same amount of capacitance for much higher DVDT. So now actually you can get more than tens of amps of current flowing through this parasitic capacitance to your heatsink, which is grounded for safety purposes. And so then that will couple through your control circuitry. So that's also something that needs to be considered. So I just want to give a quick background too on commercial medium voltage power modules. So maybe some of you are aware of the press pack. So this does not use any wire bonds. It actually sandwiches the chip between two molybdenum plates. Molybdenum is a type of metal. And then it has these they're called like common contacts that interface with all these die. So all these are put in parallel to increase the current. So advantages, no wire bonds, so higher energy absorption during faults. Double-sided cooling, so you're cooling from both the bottom and top, whereas before I showed you that you only cool from the bottom. Symmetrical contacts to all the die, so you avoid some of the asymmetry issues. Disadvantages, though, it's not isolated from the heatsink. It has actually, in order to make sure that those contacts are in good contact with all of those die cells, you need to have actually a very complex structure outside to make sure that the force is uniformly distributed so that you don't have, say, if it's kind of distributed in an angle, then maybe you're contacting some die better than others. And that's not good for cooling purposes as well as the electrical connection. So to solve that, ABB came out with what's called a stack pack. And so there are these very large spring features here, and they contact each die individually. So the spring will help with that kind of asymmetry when it comes to the force. But they're very high stray inductance, all of these modules, and quite large in size. So what's been done for high voltage silicon carbide power modules? I showed you the first generation power module. At the time, these were brand new 10 kV devices, so they didn't want to do anything overly complex with the power module package, which is understandable. So they just used standard packaging technologies and footprint. And the good thing is that it was at least isolated from the heatsink. Disadvantages, wire bonds, large footprint, high stray inductance, and very high asymmetry among the parallel die. So there were 12 die in parallel, and actually there's more than 2 times difference to the power terminals. So that also causes imbalance, as we saw before. And then last year, Wolfspeed released a 3rd generation 10 kV 240 amp module. So we actually also have these in our lab and are testing them now and are building a new PEB, hopefully with better EMI, which should be completed in the next year or 2. And so this one's a little bit better. So it has lower stray inductance, and this kind of sub-module arrangement. So you can see these terminals are kind of distributed throughout instead of just at one end. So that helps with some of the asymmetry. But it still has large parasitic capacitance to the heatsink. And again, that's a huge issue for common mode currents. It's going to prevent you from being able to actually operate your converter in the end. Okay, so that brings me to the objective of this work, which is to design a high-density, high-speed 10 kV silicon carbide MOSFET power module with still keeping in mind the system integration, and so looking at the EMI and things like that. So the Challenges, high density. So we're achieving that in one way by eliminating external diodes. The nice thing about silicon carbide MOSFETs is that you can use their body diode and also reverse conduct through the channel. So I'll show that later, that you can get very low on-state resistance just using the silicon carbide MOSFET body diode and reverse conduction. You don't necessarily need that anti-parallel diode. So that cuts the size of your power module in half. Then again, high density plus high voltage equals high electric field. So how are we dealing with that? We're actually doing a few methods. One is to stack those insulating substrates, so having two on top of each other in just a single one, and I'll show why. And then also developing new kind of termination structures as well. High DIDT and DVDT. So we're eliminating wire bonds, creating a scalable design that has a lot of symmetry as well so that you avoid this imbalance, and embedding decoupling capacitors and integrating a common mode screen to hopefully mitigate some of these issues that we saw before. Okay, so this is the designed power module. So I'll go through it kind of in phases and build it up as we're going. So it's a half-bridge power module, so there are two silicon carbide MOSFETs here, one here and one here. And then we have at the bottom the insulating substrate, and these colors correspond to the nodes in the schematic at the top right. So we've got the high side switch here and its drain contact, and the low side switch and its drain contact. And these are 10 kV 350 milliohm silicon carbide MOSFET die. And these are their static characteristics. So this is in the forward direction in the on state, and this is the reverse conduction through the channel. So in the on state at 20 volts gate source voltage, you get this kind of drain current performance. And then if you have your device, during the off state, if you just want to conduct through the body diode, this is the kind of resistance you would get. And you see that your resistance actually decreases significantly if you turn on the device and reverse conduct through the channel instead of the body diode. So that's a huge benefit that silicon carbide has. So you can get higher power density, about 20 millimeters by 35 millimeters. So this is very tiny substrate, about this size, and lower cost. So these silicon carbide MOSFET die are about $1,100 a piece, and the 10 kV silicon carbide Schottky diodes are about $600 or $800 a piece. So you can at least reduce the cost of your power module by eliminating those diodes. So we're also stacking these substrates here. So this is what that looks like. So we've got two metal ceramic metal substrates, one on top of the other. And there are three main reasons for this. The first is to reduce the peak electric field. Second is to increase heat spreading, and third is to create a common mode screening effect. So I'll go into all of these now. So it was shown in the literature that for standard metal ceramic metal, this is the electric field distribution for that. And if you stack two ceramic substrates, now you can see the electric field is kind of more evenly distributed throughout the two ceramics. And they actually also did partial discharge tests. So what they do is basically apply a voltage and measure the partial discharge current. And so that voltage at which the partial discharge occurs is called your partial discharge inception voltage, or your PDIV. So this is plotting the partial discharge inception voltage for several different cases. And so this first case is with 0.3, let's just call it 0.3 millimeter thick alumina ceramic. And then the second case is 0.6 millimeter alumina ceramic. And the third case here is for 2 of the 0.3 millimeter ceramics. And you can see that actually when you have two stacked ceramic substrates, you actually get 2 times higher partial discharge inception voltage. So what that means is that instead of seeing partial discharge at 3 kV, you're now seeing it closer to 6 kV, which is a significant increase. Okay. So, but this was kind of an oversimplified case. So in an actual circuit, this top metal pattern, this top metal is patterned. That's where your whole circuit is formed for your half bridge. So you actually have multiple potentials on top. So if you just kind of leave your circuit like this middle metal layer is left floating in this case. And if you have multiple layers and multiple patterns on this top metal, then it's not going to float to a potential that will actually give you a benefit. And so that's what we were demonstrating in this work. So if you have the single substrate, this is electric field simulation. So the single substrate, you can see that high electric field at those triple points. Then if you add your second substrate and leave that middle layer floating, so this is still a simplified case. I'm just showing now 2 patterns with your positive and negative DC bus on top. You can see your electric field is still heavily concentrated in this area. And then if you connect your middle metal to half of the applied voltage or half the DC bus voltage, now you're getting much more uniform electric field distribution, and the electric field at that critical triple point region is now distributed at all these corners, which is significant. And we also did partial discharge tests to verify this. So this is the setup. So we've got a high pot tester, high voltage probe, and we use a high frequency current transformer to measure the partial discharge signals. And this is an example waveform. So this is with a line frequency AC excitation, and then these are the partial discharge events here, these little current spikes. And so this is plotting those partial discharge inception voltages for 3 different cases. So, and the blue is for an AC excitation line frequency. The orange is for a DC excitation. So you can see that when you stack 2 substrates and leave that middle layer floating, you only get about 15% increase in your PDIV, which is still good, but maybe it doesn't justify the cost or processing of that extra ceramic substrate. But if you connect that middle metal layer to half the DC bus, then now you get actually more than 60%, closer to 70% increase in your PDIV, which is starting to be significant. But again, as we mentioned before, so your thermal interface usually comes from that bottom, or the main region for your main location for your heat extraction. So we need to make sure that by adding that second ceramic substrate, we're not significantly hindering the thermal performance. So this is a 3D steady state thermal simulation. So these here are the semiconductor die. And this is for the single insulating substrate case on the bottom, and the peak junction temperature is about 180 degrees C. Then when you stack 2 substrates together, the peak junction temperature actually decreases by 10 degrees C to 170. And the reason for this is because of the added heat spreading that you get from that second insulating substrate. We're using aluminum nitride, which has very high thermal conductivity. If you use some different ceramic materials, you don't get as much of a benefit. It's also, of course, going to depend on your heat transfer coefficient of your cooling system. But in general, it doesn't necessarily hinder the thermal performance, which is a good sign. Okay, and then for the interconnection, we're using molybdenum posts instead of the wire bonds. And the reason for using molybdenum is actually its coefficient of thermal expansion. So metals typically have a very high coefficient of thermal expansion, means they expand and contract a lot as temperature increases. Whereas semiconductors and ceramic materials, the blue and orange bars, have much lower CTE. And so that kind of mismatch causes a lot of thermomechanical stress on the devices and can cause reliability issues. So we're using molybdenum because it has much lower CTE and very close to that of silicon carbide. So with this, by eliminating wire bonds, you can increase your power density, reduce your parasitic inductance, and also increase the reliability, because wire bonds are also not known for being reliable. They break and lift off very easily. And then we use a top insulating ceramic substrate to finish that kind of interconnection. So that kind of connects the source of the high side switch to the drain of the low side switch. So the green here will connect to the green here through this upper connection. And there are vias in these ceramic substrates to bring all the electrical connections to the top. Okay, then also by having this top insulating substrate, we can also have a little bit higher layer of integration, level of integration. So we're also embedding decoupling capacitors. And what that does is it gives a very low impedance, high frequency power loop inductance, power loop path. So we get a power loop inductance of about 4 nanohenry. And the gate loop inductance is also small, around 3.8 nanohenry. So again, this just gives lower inductance, reduced electric field, common mode screening, and improved current sharing. So that's all because of these capacitors. So as I mentioned before, we need to connect that middle metal layer to half the DC bus. Well, how do you do that? So by having 2 capacitors in series, now you have access within the power module to half of the applied voltage, or half of the DC bus voltage. So that's realized through vias in the ceramic substrate. So here's a look at that. So this is the midpoint of the 2 capacitors, and that everything that's the same color is the same potential. So now you've got that connecting to the middle metal layer. And so that serves, again, a few purposes. The first purpose is reducing the peak electric field at those triple points. The second is also now it forms a common mode screen. So now you've got this parasitic capacitance at your output here. So this potential is always jumping, right? So based on which switch is on, this is either at your positive DC bus or your negative DC bus. So there's always a dV/dt transient happening here. And so when you have these parasitic capacitors in this ceramic material, then that forms a path for that common mode current to flow again through the system ground. When you have two ceramics stacked on top of each other, that's good. You've got now two capacitors in series, so your impedance is higher. But if you can take it one step further, and by having this kind of connection back to the DC bus, then you can divert a lot of that common mode current that's generated back to the DC bus and have it stay within the power module, and very little of it will go now to the heatsink. And of course, this is going to depend on the impedance, though, of this kind of return path. So if the impedance of your screen or your return path is low, then you can have more of that current being diverted. If that impedance is higher than the impedance that the current will see to the ground, then obviously it's not going to be very effective. So having it kind of all internal to the power module and really an integrated solution is really helpful. And we demonstrated this. This was demonstrated on a 1.2 kV silicon carbide MOSFET. So this is the noise spectrum through the Liznitz right here, the noise that we're measuring when you don't have any screen. So you just have that one parasitic capacitance to the ground. Then when you have two ceramics now on top of each other, again, your current's a little bit, your impedance is now higher because you have two capacitors in series. So you get some reduction at high frequency. And this resonant peak shifted because of your embedded decoupling capacitors. But then if you just take the added step to connect those two, so connect that middle metal layer to half the DC bus, now you can get even further reduction in the noise at high frequency. For this example, we got 15 dB reduction, which was about 50%. Okay, and then I also mentioned that these embedded decoupling capacitors can help with current sharing. And that's because this module is actually scalable. So you can kind of just keep adding the devices in this direction, and they're all, because each MOSFET switch pair has its own set of decoupling capacitors, so actually the power loop does not increase as you add more modules in this dimension, and the gate contacts are also distributed throughout. Okay. And
quick question.
yeah.
You can go back and,
Yeah.
those black things on top, are those balancing resistors?
They are, yes.
So I'm curious, how much do you have to, the size of those? Is there appreciable static power dissipation there?
No, actually, the capacitors that we're using are quite good. So the resistance of these balancing resistors can be like 10, 15 mega ohm. Yeah. Yeah. It can actually be higher, honestly, too. These capacitors are quite good. And we've actually we fabricated one module without the resistors and still didn't see any balancing issues. So, yeah, good question though. Okay, so also an issue with high density is obviously when you have higher power density, now you've got higher heat flux density. So now you've got a smaller area that you need to extract the heat from. So we're using, and this is a big contribution from the University of Nottingham. They've worked quite a bit on this kind of cooling system. It's direct substrate jet impingement cooling. So we're actually not using a base plate like you would typically use to spread out the heat in the power module. Instead, as you can see from the system, or this image, so we've got the semiconductor die here, and this is maybe your ceramic substrate in our case. And so your your cooling liquid will come here, and then you've got these holes here that will impinge the liquid directly underneath your semiconductor device for more efficient cooling. Otherwise, typically it'll just pass underneath. This will actually impinge underneath the device, and then you've got your heat transfer happening in this area, and then the mixing of your working fluid. So this one was actually custom designed for our power module, and it's actually integrated inside the housing material. So we 3D printed this power module, this housing material, not the power module, sorry. And then you can see the inlet and outlet. So this is a cross-section view. So the semiconductor die are here and here. So you've got your inlet, so the fluid will come in here, impinge on the semiconductor, come back, impinge on the second one, and go back out. We also looked at ones where it would just be two different flow paths, so you wouldn't have to go through both. But that's another story. I can go into more detail on this cooler later if you'd like. So it's just greater heat transfer coefficient. You're getting actually like tens of thousands of watts per meter squared Kelvin heat transfer coefficient, and it's very high density and a nice integrated solution. So this is a look at the 3D model of the final power module. So it's great. It's very high density, but one of the issues, and it's got 6 semiconductor die per module in the full module. But one of the issues is the termination. So you've got 10 millimeters now for 10 kV. How do you terminate that? How do you connect that to the rest of your system? This is a huge issue. So if you look at any high voltage connectors, or the majority of power modules use bus bar connections. And so when you get to higher voltages, you need to worry about creepage and clearance distances and standards. And so those will significantly increase the size of your module. I think for 10 kV, it wants about 80 millimeters spacing. You can see the size of the power module is 50 millimeters. That's not possible. So we're looking at new termination schemes for that. And any high voltage connector that's already isolated, that's sealed, is much bigger than the size of this power module. So we had to really be creative with this part. And this is something that we're still working on. So this is a top view of, So this is a top side view of these two patterns here. So this is electric field simulation. So say we've got 10 kV across these two patterns. And again, they're about 10 millimeter spacing in these areas. So this is a look at springs. So we looked at bus bars, but because of the sharp edges, they're not ideal for high voltage. So we looked at more rounded geometries like springs or pins, for instance. And the electric field strength of air is 3 megavolts per meter. And so you can see that in these areas, we're actually exceeding that. So that means that you would have partial discharge in the air. You would actually be able to visibly see sparks and cracking. So we looked at a few different things. Okay, so what if you coat these springs with a dielectric material? So if you use something with Teflon that has a low permittivity close to that of air, then you can get some reduction in the electric field in the air. But you need to be careful. So if you use a dielectric such as like silicon with a higher permittivity, then it has almost no impact because it's not going to drop a lot of the electric field over that because of the higher permittivity. The electric field will go mostly in the air because of that. And then also looking at, can you actually encase now, so you've got these pins. What if you put like an elliptical shield around them that's at the same potential as those pins? And that way, the electric field within that area is not essential, it's not critical because it's all at the same potential. And this way you've got a lower curvature at the outside, and so your electric field is now much more uniformly distributed. So we're trying to look at different methods like this for these terminals. So this is a cross-section view of that. So these are the elliptical shields here, and these are the springs. And so what if you have now a PCB that can come and mate with the housing material, so it's sealed, so that way you don't need to worry about creepage between this terminal and this terminal. But you still have these air gaps here. And any place you have air, you have a place for that partial discharge can occur. So we again looked at electric field simulations. So if you have 10 kV between here and here, you can see internal, because of those springs, there's not a lot of significant electric field. But still in these air gaps here, you have some high electric field that exceeds the breakdown field strength of air. So we looked at some field grading methods. So what if we put these field grading plates inside your PCB or bus bar? And then that can actually shift the electric field so that instead of being in the air, now it's in your bus bar material instead, which has a much higher electric breakdown field. So just kind of looking at different options like this, looking at both from the two ends. So we've been researching a lot on classical techniques for like high voltage engineering and like donuts and corona rings and things like that, and also things down at the semiconductor level and how they do edge termination and field grading at that level, and trying to apply both of those. So that's been something that has been really interesting, I think, for me. So this is the fabricated power module. This isn't the full power module that I showed you with the 6 die in parallel, or the 6 die total. This is just 2 die for now. They're $1,100 a piece, so we just wanted to get comfortable with the fabrication first. So the 10 kV die are here. These are the molybdenum post, and then these are the stacked substrates. And then this is it in the housing with the embedded decoupling capacitors and the spring terminals. And then here is it with the integrated cooler as well. So we did basic static characterization. So these are kind of dummy die that the manufacturer sent us for free. So they don't, I call them kind of dummy in parentheses because I don't think they're dumb. They actually function very well. They're not mechanical switches, like mechanical die that doesn't block any voltage, doesn't conduct current, doesn't turn on. These actually are functional. They just don't block the 10 kV. They block about 6 kV. So could still be used for initial testing. And that's what we did. So this is kind of the double pulse test setup that we did at the University of Nottingham. So we've got a 10 kV power supply, some DC bus capacitors. The power module is very small in this area here. Your high voltage probe and your inductor, and we used a Wolfspeed gate driver. So these are the switching results. So we couldn't measure the current because of the embedded decoupling capacitors. That's something that we're going to work on. We're going to do another module without the capacitors and try to measure the current that way. So this is the turn-on waveform. So this is the gate source voltage waveform. The ringing is because of the connection to the gate drive. It wasn't ideal. That's something that we need to work on, a better interface for that. But the drain source voltage is what you should really be worried about. So this one is switching in 2.5 kV in 10 nanoseconds. So that's about 200 volts per nanosecond switching. The reason we stopped at 2.5 kV is actually because the DC bus capacitors were limited to 2.7 kV. So Nottingham didn't have access to higher voltage capacitors. At CPES we do, so we're going to repeat the test there at higher voltages. And then this is the turn-off waveform. This one's a little bit slower, about 43 volts per nanosecond. Still substantial. You're still switching tens of kilovolt in about 50 nanoseconds. And this is all with 0 ohms external gate resistance. There's very little voltage overshoot. I think it was like 3% voltage overshoot or 2%. Yes?
So I'm just wondering, like, why the gate voltage is connected.
Yeah, so in the off state, the driver we use uses a -5 volts. Yeah. So for silicon carbide, they tend to use -5 volts just for safety purposes, and it also drives the devices faster. So it helps them turn off a lot faster when you drive it to -5 instead of just to 0. And it just gives you a little bit more margin because the threshold voltage for these devices is lower than silicon. So it's about 3 to 4 volts they'll turn on or start to turn on. They actually don't fully turn on to like 7 volts, so it's not completely necessary, but it's just a safety feature. Yeah.
Is there any uncertainty there in terms of how good those meters are? Or those meters are quite good?
The probes that we were using?
Yeah.
Yeah, they were actually, so that was the first thing that I checked, and we were using a 400 megahertz probe, so it should be able to measure this pretty accurately. Yeah. We've used those probes actually for lower voltage, similar tens of nanosecond switching for lower voltage switches. I didn't expect to see it for 10 kV, but yeah. Okay.
How frequent or is that continuous measurement that you actually get?
This was a double pulse test. So this was just 2 pulses to measure the turn off and turn on waveform. That was it. Yeah. Because the module that we tested actually didn't have the cooling system, so we couldn't operate it continuously. And also in Nottingham, they don't have high power, high voltage power supply. So they don't have a way to have the converter running continuously, unfortunately. It's something that they're working on. At CPES, we have something that we can throw together, though, to make that work. We have some power supplies that we can use.
You did this work in Nottingham because you don't have the same facilities at your university? Or?
So we did this in Nottingham because they have a little bit more packaging, a little bit more advanced packaging facilities than we have at CPES. And right now at CPES, I'm kind of the only student working on this, and this is a collaborative project. So we actually started designing this module 2 years ago, and I actually went to the University of Nottingham for 6 months to start designing this with their faculty, with their postdocs. So they actually have a bigger team there working on it, whereas at CPES it's just me. So it would have taken me a little bit longer to actually fabricate the power module. So I went there and built it with them together. So we jointly built it in Nottingham, and then we were all really eager to test it right away. So we just put together whatever they had there. But actually, testing facility-wise, CPES has more suitable equipment for that. So we're actually going to start testing the power module, I think, at CPES.
Can you detect the British accent of the packaging or not?
Detect the British accent in this package? Yeah, maybe, sure. But it was nice. So they even, on the power module, there's the, you can't really see it, but there's both the CPES and Nottingham logos embedded in there. So it really is a joint project, which has been really nice. So they have a really strong group in terms of packaging and a lot of experience there and quite a lot of researchers dedicated to that. And CPES, we don't have as many. We have students that focus on like a specific area. So for instance, in sintering or in having the stacked DBA substrates or stacked ceramic substrates, we actually needed to have a good way of bonding them together in order to get that good thermal performance. So we have a lot of students that are skilled at silver sintering. So we worked with them really closely to develop a method that would get a really low voiding content for that silver sintered layer. So we have several students at CPES that are good at kind of the individual components and materials, but for the full fabrication of the power module, the full assembly, I would say Nottingham is definitely better suited for that. Yeah, thank you. Sorry, I'll skip through this. And then this is kind of one of the last slides I have. So just a comparison to summarize. So the first generation 10 kV 120 amp module from PowerX had quite high parasitic inductance and high asymmetry. The gate inductance wasn't too bad, and it had high parasitic capacitance to the heatsink, about 370 or maybe even a little bit more to the heatsink ground, and quite low power density. The new generation, third generation modules from Wolfspeed have lower parasitic inductance and increased power density, more than 4 times increase compared to the first generation, which is great. Then we're also building, or we also already built a wire bonded module as well. And that's for more fair comparison to the sandwiched kind of structure that I showed you today. Because that'll serve as kind of the benchmark to really justify this more advanced packaging technology. So that still has several benefits over the commercial products. But then in the end, the structure I showed you today has the most benefits. Specifically, it has 5 times lower parasitic inductance, 11 times lower parasitic capacitance, and not to mention the integrated common mode screen. So this capacitance is kind of irrelevant. And then 4 times higher power density as well. So the design power module has high power density because of the lack of external diodes and wire bonds. It has low electric field concentration because of those stacked insulating substrates. High energy absorption, sorry. Low EMI because of that integrated common mode screen. Balanced current sharing because of the symmetric layout with the embedded decoupling capacitors, and fast switching speed because of the low parasitic inductance and high frequency, low impedance power loops, and then high heat extraction because of that custom designed direct substrate jet impingement cooler. That was a mouthful. Okay, and there was a huge team behind this. So there were several students at Virginia Tech that helped with some of the subcomponents of the module, and then also quite a few people from the University of Nottingham that have helped. DOA donated the substrates with the vias in them, and Wolfspeed for helping us with the die and everything. The Office of Naval Research has been funding this also for a while. So thank you all for your attention. Yes.
What was the most challenging part of this project?
Most challenging part?
And how much background do you have, like, in materials to do this kind of stuff?
Right, so actually, as you've kind of seen, I touched on a few different areas. So there's definitely the material science, there's more physics and high voltage engineering when it comes to the partial discharge stuff. Then also, obviously, the EMI kind of work and electrical work. So it kind of touches on several different fields, heat transfer. I would say the most challenging for us at CPES was the partial discharge. So building up that testing capability hasn't been easy. We have a student that's fully dedicated on working on the partial discharge because we do see a huge opportunity for these power electronics, in higher voltage applications. So we do want to start building up that capability, but it has been a challenge. So I'm not that familiar with all these electric field simulations and field grading methods and looking at, edge termination techniques and high voltage engineering techniques. So that's been really exciting, but also a huge challenge as well. Yes? Oh, sorry.
Well, you could go first.
Yeah.
I was curious, are you shooting at a specific higher level you want to get to, or are you just going to go as high as you want?
In terms of voltage?
Or power.
Power? We would have liked to have like a 100 amp power module, but because of the cost of these die being $1,100 a piece, we said, okay, if we can demonstrate a power module that has 3 die in parallel per switch position, then we can show the good current sharing between them at still a reasonable cost. But ideally, we would love to have several hundred amps or higher for an actual application.
Still at the 10 kV level?
For now, that's at the module level, yes, just 10 kV. And then at the system level, you can have these power electronics building blocks and put those in series in order to increase the voltage capability. But right now, 10 kV die are the highest voltage rating that we can get. They do have experimental work on like 15 kV silicon carbide MOSFETs and 15 kV silicon carbide IGBTs, but they're not as easy to acquire right now. But we would love to go higher voltage. So when those do become available, I would definitely love to get our hands on them. Yeah.
Was there a question here? Otherwise, yes. So would you mind you go to slide 5?
Do you mind if so I don't have to click back there?
Oh, went off the screen.
Yeah, it's okay. There we go. Slide 5.
It shows the bank and energy actually larger than silicon carbide.
Yes.
Isn't that supposed the GaN device should have higher electric field than silicon carbide?
Oh, okay. I did change around these numbers a little bit, so maybe I typed an error when I plotted that. Okay. Yes, I think you are right. It should be at least very close to silicon carbide. Yes.
So if based on this point, then that means the electric field for gallium nitride and silicon carbide are similar.
Mm-hmm.
Then why do you choose silicon carbide instead of gallium nitride?
Yes, very good question, actually. There was another question about this earlier. So the main answer is that right now gallium nitride is just lateral. So if you increase the voltage, then you can't scale to higher voltages in an economical way. You basically need to increase the size of your die. So silicon carbide devices are vertical. So what that means is that you just have to increase the size, the thickness of your device, the thickness of your drift region, and you block the voltage vertically. And that's why your drain contact is on the bottom. So once vertical GaN does become an option, then they can definitely go to higher voltage. But right now with lateral GaN, it doesn't make sense. But there are people working on vertical GaN, and I have seen projects for developing 10 kV vertical GaN. It's starting with diodes right now. Those are a little bit easier. Still a challenge, but they're still very far from being. The idea is that this package, though, could be adapted for GaN at some point, too. It's really just kind of paying attention to high voltage and high speed. So if you can have a power module capable of that, then any device that's high switching speed and high voltage should be able to fit in this module. Mm-hmm. Yeah.
Did you go to your table of comparison?
Yeah.
Slide. Yeah, so one thing you mentioned, which I really do agree with strongly, is that the integrated column on screen, from an EMI point of view, is going to be essential to use these packages. And you also look to the fact that your 35 picofarad there is kind of not the right metric because you have the return path for the common current. What do you propose as a metric? How should one quantify the substantial benefit of your power module compared to others? Do you have a way to sell that in a number to a marketing person?
It's hard to say because it would be something that I think you would just have to test in the end. You could maybe come up with a number based on like the impedance of your return path of like some ratio perhaps, and put that in there, or like a derating factor. In the end, I think the best would be if you could actually say like the noise at high frequency and what those are and the reduction there. But you can't really do that without testing all of those. So.
Right. There's no DiMarino bigger merit coming up.
Not yet,
Okay.
but that is a good point. Yes. Yes.
So this stacked substrates,
Uh-huh.
you actually go in and clamp the voltage in the intermediate layer. If I compare that to high voltage bushings where they do voltage grading, multiple layers,
Uh-huh.
I think there, if I'm not mistaken, they let the capacity voltage division.
There's still some resistance division.
Right, but they don't go and impose the voltage, right? It's a naturally
Right.
distributed.
And that works if you have symmetry in your isolation capacitances. So I actually did a lot of electric field analysis with this. But the main issue is that, so like we saw here, you can have that. So without having to clamp this metal, if you have this kind of symmetry where this isn't patterned, so this is just a single block of metal, this is just a single block of metal, they have some differences in the extent. But basically you have pretty good symmetry, so this metal layer will kind of just float to the potential it needs to balance these out. But the issue is that when you have a complex pattern like you have for a power module on the top side with multiple different potentials on it, then your capacitances are all over the place. And so your isolation capacitance, actually, as you saw here, because your isolation capacitances are different for all these three regions, this middle metal doesn't float to a potential that actually helps you. So it doesn't uniformly distribute the electric field. And so by clamping this, then you kind of get that advantage because you've got all these different potentials here. So if this is 10 kV, then for this to be beneficial, this only floats to about, I think, like 300 volts or something. So it's basically not giving you any benefit. It's very mild, as you can see from the electric field here. It's not very strong at all. Whereas when you put that at 5 kV, for instance, then now you get that electric field distribution. But I agree with you, if you have that symmetry in the vertical dimension, then yes, naturally you shouldn't have to clamp it.
So the 300 volt you got by test floating voltage.
So actually I compared a lot of things. So I did it in simulation, calculation, and experiment, and they all agree. Yeah.
I assume that's a little off base because you're showing a plus VDC and a minus VDC and a VDC over 2.
Yes.
You really are meaning a midpoint between the plus and
Oh, this floating here? Which, sorry.
In other words, it's really plus TC and 0 and VDC over 2 or something like that, right? You don't have plus 10 kV and minus 10 kV.
No, sorry. Yeah, you're right. The nomenclature I used maybe isn't the best. No, this is 10 kV, 0, and 5 kV. Yes. Sorry about that. That's a really good point. Thank you. I should be more clear about that.
Bottom is at 0.
This is at 0, and this is at 0. So we've got 10 kV, 0, 0, and 5 kV. And so when this is at 10 kV, 0, and 0, then this, because of the larger size of this heatsink, and because you also have 0 here, then this doesn't float to a very high potential. This will only float to about 300 volts because this voltage here isn't enough to really bring it up because it's such a small area, and you've got just as much area at that 0 volts on the top side. So that's why. But if this were all 10 kV here, and this were floating, and this was all 0, then this would float perfectly to 5 kV.
So how much of this work is patentable?
We did actually file a patent application for the common mode screen. So there was a previous patent by Infineon that did talk about a screen, but they used it's actually a quite high impedance return path because they do the connection all externally to the module. And so they have stacked substrates, but they propose to connect that middle metal layer either to the positive or negative DC bus. So then that second substrate is basically useless. It's really not giving you any benefit in terms of electric field. And so I don't know. At CPES, the industry members thought it was worth patenting the screen.
And do you see an application of this right away for the device?
Absolutely, that one's easy to implement, I think. If you're willing to, it depends on the application. So some applications, the cost of another substrate maybe isn't worth it. For these 10 kV power modules, you can pretty much do anything. The cost of the package compared to the cost of the die is negligible. So adding a second substrate isn't bad, but you have to think kind of in the actual application, are they willing to pay a little bit more for the power module design and then have the added benefit of maybe being able to reduce or eliminate their filtering at the system level. So as long as you kind of can show them the system level benefits, I think it should be fine. But it's relatively easy to implement into a power module, and you don't need this kind of sandwich structure. You can also have it on a planar module as well with wire bonds. We've also demonstrated that, and it works. Yes?
So you mentioned the use walkie gate driver for this?
Yeah.
That's external to the power module.
Right, right.
And you showed it's responsive non-heavy field conductor. That includes everything from gate driver.
No, that was just for the internal to the power module. And so we just used the Wolfspeed gate driver because it's honestly just what Nottingham had at the time. So at SI PES, we're actually designing our own 10 kV gate driver. So that'll have a lot better, I think, gate loop for from the gate driver side. And so I want to work on a PCB design and integrate that, make it more suitable for the power module so that we can completely reduce the overall gate loop inductance. Yeah. So the initial tests I showed were really just initial. It was done very quickly. We were all very eager to just switch the module. So I would have liked to spend more time and actually properly design a gate driver, but they were like, no, we have one. Let's just do it. And I can't blame them for that. I was really excited to see it switch too. But the next step would be to design a proper gate drive that will interface better with the power module instead of having like wired connections. Yeah.
When you say design a new gate driver, you mean
Yeah.
actual IC or just a way of embedding it inside your module?
So not embedded within the power module, and not designing the IC itself, but using commercial like gate driver ICs and developing the circuits around it. So we're working on actually for Wolfspeed's third generation 10 kV power module, we're actually working on a gate driver for that with isolated power supply as well. So it'll have Rogowski coil current sensing that's embedded within the PCB. So you can sense the current for all of the through all of the sub-modules in the gate driver, and then that can be used both for, it's a very intelligent gate driver actually, and it can be used both for current sensing for fault protection as well as for control. So,
Thank Christina for sharing about her work.